Today in lab we'll be titrating acetic acid and then analyzing the data. In the first part of the lab you'll be preparing an approximately 0.1 molar solution of NaOH. You will then standardize that solution and then titrate acetic acid. The acetic acid solution is pre-made for you and is of an unknown concentration, so you'll be using your data to calculate the concentration. In step 1, we'll be adding 500 milliliters of distilled water to a polyethylene bottle. We will then add 2.6 milliliters of 50% NaOH to the bottle. We will then cap the bottle, label it as the NaOH solution, and shake. First, measure out 2.6 milliliters of 50% NaOH into a 10 milliliter graduated cylinder. Measure out 500 milliliters of distilled water in a beaker. Add the water to a clean bottle. Add the 2.6 milliliters of the NaOH, cap the bottle, and shake. We now have our 0.1 molar solution of NaOH that we will standardize in step 2. In step 2, we'll be standardizing our NaOH solution. We'll first use an analytical scale to measure out 0.5 to 0.7 grams of potassium hydrogen phthalate, also known as KHP. We'll then place that KHP in an Erlenmeyer flask and add 50 milliliters of distilled water and 2 drops of our indicator phenolphthalein. We'll then rinse out the burette with our NaOH solution to make sure it's not contaminated with anything else or the concentration is not affected by excess distilled water. We will then record the volume of NaOH in the burette, titrate until we get a faint pink color, record the final volume. We will do this process a total of 3 times so we can average out our molarities of NaOH to get a more accurate result. Before performing the titration, we need to ensure that we can properly read a burette. 0 milliliters is at the top of the burette and is read downwards, unlike most other instruments in the chemistry lab. For example, in the picture we can see now, we would read it as 21.30. The meniscus falls on the third mark below 21, and we add a 0 at the end because the first uncertain digit is our last significant figure. We are now ready to begin step 2 of our titration. First, we're going to measure out the KHP using an analytical scale. Open up the scale, place an empty weigh boat in it, close it, and press tare. Once the analytical scale reads 0 grams, we can now add some KHP. We want approximately 0.5 to 0.7 grams of KHP. Carefully and slowly add and subtract KHP until you get a mass within the range that we want. Then record the exact mass in your lab notebook. Place the KHP from the weigh boat into an empty Erlenmeyer flask. Measure out 50 milliliters of distilled water in a graduated cylinder. Pour the distilled water into the Erlenmeyer flask. Swirl until all the KHP has dissolved into the water. Then add 2 drops of phenolphthalein into the Erlenmeyer flask. We will now clean our burette with the NaOH solution. Place a funnel in the top of the burette and pour some NaOH solution into it. Then pour the NaOH solution into a waste beaker as you twist the burette. Repeat the process. Pour some more NaOH into the burette. Hold the burette over the waste beaker and open the nozzle. Let all the NaOH drain out. Place the funnel in the top of the burette and fill the burette full of NaOH solution. Make sure that NaOH does not go above the 0 marking on the burette. Then place the burette into the butterfly clamp. Then place the Erlenmeyer flask with the KHP distilled water and indicator underneath the burette on the stir plate. Place the stir bar into the Erlenmeyer flask and turn on the stir plate. Now measure the volume in the burette and be sure to use the meniscus for your reading. Record the volume in your lab notebook. Now open up the nozzle of the burette slowly. We want to establish a slow and steady drip into the Erlenmeyer flask. This should be the approximate pace of your drips. As soon as you begin to see a faint pink color, close the nozzle. If the pink color stays, don't add any more NaOH. It may help to put a piece of white paper underneath the flask to see the faint pink color. Then record the final volume of NaOH in the burette. Repeat the process 2 more times. In step 3 of our procedure, we'll be titrating the acetic acid. You'll be using a solution of acetic acid that was already prepared for you and is of an unknown concentration. You'll measure out 50 milliliters of that acetic acid solution and add it to a 100 milliliter beaker. We then want to set aside that beaker while we calibrate the drop counter and set up our apparatus. We'll first rinse our reagent reservoir, similarly to the way we rinse the burette in step 2. We will then place the reagent reservoir into the apparatus and set up everything in the apparatus except the pH meter. Then place a clean 10 milliliter graduated cylinder beneath the drop counter so that the drop goes from the reagent reservoir through the slit in the drop counter into the graduated cylinder. Then go onto the drop counter and start the calibration. You want to first make sure that the bottom valve is open while the top valve is closed. After you click start, slowly open the top valve so that it's about 1 drop for every 2 seconds. You then want to close the bottom valve when the volume is between 9 and 10 milliliters in the graduated cylinder. You then want to enter the volume of the NaOH collected in the graduated cylinder into the Logger Pro. Once we have calibrated the drop counter, we will then add the pH meter back into the apparatus and perform the titration until the pH is approximately 12. This is a picture of our apparatus. At the top we have our reagent reservoir clamped down. Below that is the drop counter, and within the drop counter is a slot to put the pH meter, and below that is our beaker, which is on a stir plate. The drop counter and the pH meter both have cords that plug into the Logger Pro. So you're first going to rinse out the reagent reservoir with the NaOH solution, set up the drop counter, calibrate the drop counter, add the pH meter, measure out 50 milliliters of the acetic acid solution and pour it into the beaker, and place the beaker underneath the drop counter and the reagent reservoir. Fill the reagent reservoir full of the NaOH solution and make sure that the drip will still go down through the slit in the drop counter. Put the stir bar in the beaker and turn on the stir plate. Press start on the Logger Pro. You now want to open the top valve of the reagent reservoir and then slowly open the bottom valve of the reagent reservoir so you have a nice steady drip going through the drop counter into the beaker. Then let the experiment run until the pH is approximately 12. You want to make sure that you're collecting data in a graph that looks similar to the one shown on the screen. We're now going to analyze our data from the titration. We're first going to find the molarity of our standardized NaOH solution. To do so, we'll take the mass of the KHP that we've measured in grams, divide that by the molar mass of KHP, which is 204.22 grams per mole, then multiply that by 1 mole of NaOH divided by 1 mole of KHP, because it's a 1-to-1 stoichiometry ratio, and then divide that by the total volume of NaOH added in liters. That will give us the molarity of the NaOH solution. We did this process 3 times in step 2, so we're going to average out the 3 trials, which will give us our standardized NaOH molarity. In our experiment, the NaOH ended up being 0.094 moles per liter. Here's a graph of our titration data. In a titration, you first see the pH increasing very slowly, which is known as the buffer region. You then see a dramatic increase in pH, and then it levels off again at a higher pH. At the center of our buffer region is the halfway point. At the halfway point, the pKa equals the pH. So in this problem, our pKa is 5.45 because at the halfway point, the pH equals 5.45. The actual value for the pKa of acetic acid is 4.75, which indicates that there is a margin of error in this experiment. The point on the graph where there is a dramatic increase in the pH is known as the equivalence point. At the equivalence point, the moles of base equals the moles of acid. On our graph, the equivalence point occurred at a volume of NaOH of 15.82 and a pH of 9.23. When you're titrating a weak acid with a strong base, as we did in this experiment, you should get a pH at the equivalence point of above 7. But when you titrate a weak base with a strong acid, you should get a pH at the equivalence point below 7. We will be using the volume of NaOH at the equivalence point to help us calculate the concentration of our acetic acid solution. Another way to see the volume of NaOH added at the equivalence point is to graph the first derivative of the pH on the y-axis versus the volume of NaOH added on the x-axis. As you can see, at one point in the graph there is a very large increase in the first derivative. This is where the equivalence point occurs. We will now use our data collected to find the molarity of the acetic acid solution we used. We know that at the equivalence point, the moles of acid equals the moles of base. In our experiment, the moles of base equaled the 0.094 moles per liter times 0.01582 liters, which was the volume of NaOH added at the equivalence point. This equals 0.00149 moles of OH minus. Since we know that the moles of OH minus equal the moles of acid at equivalence point, we can divide 0.00149 moles by the amount of acid we started with, which was 50 milliliters, giving us a concentration of 0.030 molar. We're now going to do a quick example titration problem. The problem is, what is the pH at equivalence point when 20 milliliters of 0.10 molar acetic acid is titrated with 0.10 molar NaOH. We must first ask ourselves how much NaOH must be added to reach equivalence point. Since we know at equivalence point the moles of acid equals the moles of base, and since the acetic acid and the NaOH both have a molarity of 0.10, we know that the same amount of NaOH must be added as acetic acid, so therefore 20 milliliters of NaOH must be added. So all the CH3COOH and the NaOH are used up, and 0.002 moles of the acetate ion are created. If we divide that by the 20 milliliters plus 20 milliliters, we get 0.050 molar. We now create our equilibrium equation using the acetate ion plus water yields acetic acid and OH minus. We know that 0.050 molar acetate ion is there to start, and X amount of it goes through the reaction, creating X amount of acetic acid and X amount of OH minus. We then can write our Kb expression, which is the concentration of acetic acid times the concentration of OH minus all over the concentration of the acetate ion. That equals X squared over 0.050 minus X. And since X is such a small amount compared to the 0.050 molar, we can say that equals approximately X squared over 0.050. To find the value of Kb, we divide Kw by the Ka of acetic acid, which gives us 5.56 times 10 to the negative 10. We then set that equal to our Kb expression, and we get that the concentration of OH minus equals 5.27 times 10 to the negative 6. We then take the negative log of that and get the pOH is 5.28. We then subtract that from 14 and get our pH to be 8.72, which is our final answer. You're now ready to perform your own titration.